The topic of this video will be the hydroboration of alkenes. This reaction, like oxymercuration demercuration and the acid-catalyzed hydration of alkenes, results in an alcohol product. In the general reaction, borane adds across the double bond in the first step. Borane is stabilized by tetrahydrofuran, a solvent. This addition produces a boron-containing intermediate. The boron is then oxidized away using peroxide and hydroxide ion to produce the final alcohol. Just like oxymercuration demercuration, hydroboration is a stereospecific as well as a regiospecific reaction. The major Regio isomer that is formed is the anti-Markovnikov product. In other words, the hydroxyl group is added to the less substituted carbon. This reaction is also stereospecific. The hydrogen and the hydroxyl group are added syn to one another, to the same side of the double bond. Again, in order to understand the regiospecificity and the stereospecificity of this reaction, we need to look at the mechanism. The first step of the mechanism is an electrophilic addition of borane across the alkene. The alkene attacks the boron, and the hydride that is produced attacks the carbon of the double bond. This electrophilic addition produces a transition state that looks like this. The alkene bond is breaking. The bond between carbon and boron is forming. The bond between hydrogen and boron is breaking, and the bond between the hydrogen and the carbon is forming. As this occurs, there is a slight partial positive charge on the carbon that is accepting the hydrogen. There is a slight partial negative charge on the boron. Addition of borane across the double bond happens in a concerted process, which accounts for the syn stereochemistry of this addition reaction. This produces the boron-containing intermediate that has the hydrogen and the boron on the same side of what used to be the carbon-carbon double bond. In the next step, boron is oxidized and replaced with the hydroxyl group of the alcohol. This happens without any change in the stereochemistry, resulting in a product that has the hydrogen and the hydroxyl group added to the same side of the molecule. Because the hydroxyl group replaces the BH2, it is the addition of borane to the carbon-carbon double bond that determines the regiochemistry of the reaction. Now let's look at a specific example. Hydroboration of this alkene produces a single product. It produces the anti-Markovnikov product. It does not produce the Markovnikov product as we saw with oxymercuration demercuration, or the rearrangement product we might expect with acid-catalyzed hydration. Now let's look at the mechanism. Borane can add across the double bond in two different ways. It can add with this regiochemistry, producing a transition state that looks like this, and the boron-containing intermediate that leads to the major product, or it can add with the opposite regiochemistry to give this transition state and the boron-containing intermediate that does not lead to the anti-Markovnikov product. We can understand the formation of the major product by looking more closely at the transition states. Remember that a partial negative charge forms on the boron in the transition state. A partial positive charge forms on the carbon opposite the boron in the transition state. In the transition state leading to the major intermediate, we see that the partial positive charge is forming on a more substituted carbon, therefore the more stable carbon with a positive charge, which forms more quickly, making this route the major product. Again, in the final step, boron is removed through an oxidative process to give the alcohol. You do not need to know the mechanism of this step. Just like oxymercuration demercuration, this reaction is also stereospecific. The hydroxyl group and the hydrogen add syn. Now let's look at an example reaction. If we add borane across this double bond, we get two possible intermediates. The addition of borane occurs in a syn fashion. The borane can add to the top of the double bond, or can add to the bottom. These two intermediates are enantiomers of one another. Following oxidative removal of boron, we get two possible products. Again, the products that we get are a pair of enantiomers.